light, reflection and refraction. We are able to see many things around us during the daytime, but all these things is not visible in a dark room. But on lighting up the room, we see many things. So why does this happen? Yes, it is because of the light. During the daytime, the sunlight helps us to see the objects. When light rays falls on these objects, it gets reflected. The reflected light reaches our eyes and we can see the objects. In this chapter, let us consider all the lights traveling in a straight line and learn the phenomena of reflection and refraction. Reflection of light. Surfaces like mirror reflects the total light falling on it. We are familiar with the laws of reflection. Now let us recall them. The angle of incidence is equal to the angle of reflection. The incident ray, the normal to the plane and the reflected ray all lie in the same plane. These laws are applicable to all types of mirrors, including the spherical mirrors. We are familiar with the image formation by a plane mirror. It is virtual, erect and laterally inverted. We know how image is formed by a plane mirror. In this chapter, let us learn how the images are formed by spherical mirrors. Spherical mirrors. Spherical mirror is part of a sphere. The reflecting surface may be curved inwards or outwards. The spherical mirror where the reflecting surface is curved inwards and pointing towards the center is called the concave mirror. When the reflecting surface is curved outwards, it is called a convex mirror. Now let us learn some of the important terms while dealing with spherical mirrors. The center of the spherical mirror is called the pole. It is inside the mirror and it is represented by capital letter P. We know that spherical mirrors is a part of a sphere and the center of this sphere is called the center of curvature. It is represented by capital C. Spherical mirrors are part of sphere and the radius of this sphere is called the radius of curvature. We can see that the distance from the pole to the center of the curvature is equal to the radius of curvature of the spherical mirror. The imaginary line passing through the pole and the center of curvature is called the principal axis. It is always normal to the spherical mirror at the pole. Let us do a small activity. Let us take a concave mirror and direct the sun rays to a small paper. We observe that there is a bright spot on the paper. If we leave it to a little longer, the paper burns. This is because all the sun's rays are converging to a small point, and this point is called the focal point or the principal focus of the concave mirror. Let us look in the image. The distance between the pole and the principal focus is called the focal length. The principal focus is represented by capital F and the focal length is represented by small f. The distance mn in the mirror is called the aperture of the mirror. In spherical mirrors, we take r is equal to 2f. That is, the focal point lies exactly in between the radius of curvature and the pole of the mirror. It is exactly at the midpoint. Image formation by a concave mirror. Come on, now let us learn what is the position, size and nature of the image when objects are placed at different levels in front of a concave mirror. Now let us look at this table. We have position of the object, position of the image, size of the image and the nature of the image. Position of the object. When object is placed at infinity, the position of the image is at f. The size is highly diminished and it is point-sized. The nature of the image is real and inverted. Now let us bring the object a bit closer, that is beyond C. The position of the image lies somewhere between the focus and the radius of the curvature. The size of the image is diminished and the nature of the image is real and inverted. Now let us bring the object at C. The image formed is also at the C. The size of the image is same size of the object. The nature is real and inverted. Now let us bring the object a bit closer, that is between C and F. The position of the image is beyond C, it is enlarged and real and inverted. When we place the object at F, the image position is at infinity. It is highly enlarged but real and inverted. If we bring the position of the object a bit further to the mirror, that is between the F and the pole of the mirror, the image is formed behind the mirror. It is an enlarged image, but it is virtual and erect image. Representation of images formed by a concave or a convex mirror using ray diagrams. Now let us keep the image at infinity. The parallel rays from the object after reflecting meets at the focus, and the image is formed at the focus, which is highly diminished and point-sized. Now let us keep the object beyond C. Now we see that the light ray parallel to the principal axis after reflecting passes through the focal point. Another ray which is passing through C is reflecting back in the same way. Now at the point of intersection of these two lines, the image is formed. We can see the image is real, inverted and slightly diminished when compared to the object. And the image is formed somewhere in between F and C. Let's place the object at C. The ray which is parallel to the principal axis after reflecting passes through F. Another ray passing through F becomes parallel after reflecting. The point of intersection of these two reflected rays is where the image is formed. We can see that the size of the image is same as that of the object, but it is real and inverted. And the position of the image is exactly at C. Now let us place the object between C and F. The incident ray passing through C is reflected back in the same direction. The incident ray parallel to the principal axis after reflection passes through F. The meeting of these two reflected rays is where the image is formed. We can see that the image is enlarged, real and inverted, and the image is beyond C. Now let us place the object exactly at F. Now the incident ray passing through C reflect backs in the same direction, and the ray parallel to the principal axis after reflection passes through F. We see that the lines never meet because they are parallel. So we say that the image is formed at infinity, but it is real and inverted. When the object is placed between the pole and the focal point, we see that the ray passing through C is reflected back in the same direction, and when it is obliquely reflected to the pole, it reflects back in the same as that of the angle of incidence. These lines never meet in front of the mirror, but when we extend them to the behind the mirror, they meet at a point, and this is the point where the image is formed. The nature of the image is virtual and it is erect. It is enlarged when compared to the object. The formation of the image is behind the mirror. Uses of concave mirror. Concave mirror is used in torches and searchlights. Concave mirrors are used in headlights to get parallel beam of light. Concave mirror is used by the dentist to see an enlarged image of the teeth. Concave mirror is also used in solar furnace. In solar furnace, the sun rays is concentrated to a point to produce large amount of heat. Convex mirror. Now let us study the image formation by a convex mirror. Let us see the table. Position of the object, position of the image, size of the image, and nature of the image. When the object is placed at infinity, the image is formed at the focus. We know that the focus of a convex mirror is behind the mirror. So the image is formed behind the mirror. The size is highly diminished. It is virtual and erect. Now let us place the image between infinity and pole of mirror. The image is formed between the pole and the focus of the mirror. It is formed behind the mirror. It is diminished, virtual and erect. Now let us try to draw the ray diagrams for these two situations. When the object is placed at infinity, we see that the incident rays are parallel to the principal axis. Upon reflecting, they seem to be passed at the focal point. Extending these lines, they meet at the focal point, and it is where the image is formed. It is virtual, erect, and highly diminished. Since focus is placed behind the mirror, the image is formed behind the mirror. Now let us keep the object between infinity and the pole of the mirror. Now let us pass two rays, one along C and one parallel to the principal axis. We know that after reflection, the reflected ray traces back when it is passed through C, and when these two lines meet, it is where the image is formed. The image is diminished, it is virtual and erect. Uses of convex mirror. Convex mirror are used as rear mirrors in the vehicles. Convex mirror produces slightly diminished and erect images. They have a wider view when compared to plane mirror. Thus, they are used as a rear mirror in vehicles. Sign convention for spherical mirrors. While considering spherical mirrors, we follow a certain sign convention, and this is called the new Cartesian sign convention. In this convention, we take the pole to be as the origin and the principal axis to be the x-axis of the coordinate system. Let us see some more conventions. Now look at this. The object is always placed to the left of the mirror. That is, the incident rays come from the left hand side. All the measurements parallel to the principal axis is measured from the pole of the mirror. The distances calculated or measured on the left hand side is taken as negative. The distances measured to the right hand side is taken as positive. The height above the principal axis, that is plus y axis, is taken as positive. The height below the principal axis, that is the minus y axis, is taken as negative. Mirror formula and magnification. In spherical mirrors, we take the object distance as u, image distance as v, and the focal length as small f. The mirror formula is given by 1 by u plus 1 by v is equal to 1 by f. This is called the mirror formula. All the measurements are done parallel to the principal axis and measured from the pole of the mirror. This formula is applicable to all spherical mirrors and it follows the new Cartesian convention. Magnification. Magnification is the extent to which the image of the object is magnified with respect to the object. It is defined as the ratio of height of the image to height of the object. M is equal to height of the image divided by height of the object. M is equal to h prime by h. M can also be defined as M is equal to minus v by u, where v and u are the image and the object distance respectively. If the value of M is positive, then the image is virtual. If the M value is negative, then it is a real image. Now let us learn another phenomena of light, refraction. Refraction of light. Let us observe some strange activities around us. When pencil is dipped partially into the water, it appears to be displaced at the interface of air and water. The fully filled tank appears to be raised. When lemon is put into a water, the lemon appears to be big when compared to its normal size. All these activities, the light is passing from one medium to another medium. We observe that it is changing its direction in the second medium. This phenomena of light is called refraction. Refraction is defined as bending or change in direction of light when light passes from one medium to another. Refraction of light through a glass slab. Now let us take a glass slab. Now let us pass light through this glass slab. We observe that light is shifted. At the interface, we observe that the light is traveling from a rarer medium to a denser medium, that is, from air to glass. At O, we observe that the light is deflecting towards the normal. Now let us look at the point O prime, where the light is traveling from denser medium to rarer medium. Now we observe that the light is deflecting away from the normal. Since the extent of the displacement is equal at O and O prime, it emerges as a parallel ray when compared to the incident ray. Thus we say that there is a shift in the incident ray. Now let us move on to the laws of refraction. The incident ray, the refracted ray, and the normal to the interface of the two transparent media at the point of interference all lie in the same plane. Now let us learn another law of refraction. The sine of angle of the incidence divided by the sine of angle of refraction gives a constant for a given color of light and a pair of media. This is known as Snell's law of refraction. sin I by sin R is equal to a constant. A refractive index. We know that when light travels obliquely from one medium to another medium, it changes its direction in the second medium. The extent of change in the direction of the light is given by the refractive index of that medium. Refractive index for a medium is a constant. Light travels at different speeds in different mediums. The light travels fastest in vacuum, that is 3 into 10 power 8 meter per second. The refractive index of a medium depends on the speed of light in that medium. If v1 is the speed of light in medium 1 and v2 the speed of light in medium 2, then the refractive index of medium 2 with respect to medium 1 is given by n21. n21 is equal to speed of light in medium 1 divided by speed of light in medium 2. That is, n21 is equal to v1 by v2. By the same argument, we can say that the refractive index of medium 1 with respect to medium 2 is given by n12. That is, n12 is equal to v2 by v1. If medium 1 is air or vacuum, then the refractive index of medium 2 is with respect to vacuum or air. This is called the absolute refractive index. It is simply represented as, if c is the speed of light in air or vacuum and v the speed of light in the medium, then nm is equal to speed of light divided by speed of light in the medium. This is equal to nm is equal to c by v. Refraction by spherical lens. Have you observed magnifying glass? It is thicker at the middle when compared to its edges. Using magnifying glass, we can see small things clearly. This is nothing but a simple lens. A transparent media bound with two surfaces, either of which is spherical, is called a lens. If it is bulging outwards, then it is called a double convex lens. It converges all the parallel light falling on it. Similarly, if the bulging is inwards, it is called a double concave lens. It diverges all the light falling on it. Let us learn some of the terminologies related to spherical lenses. We know that lens is a part of a sphere, and the center of the sphere is called the center of curvature, represented by capital C1 and C2. The imaginary line passing through these centers is called the principal axis. The center of the lens is called the optical center, represented by capital O. Parallel rays of light falling on a convex or a concave lens, after converging or diverging, we observe that they meet at a point. This point is called the focal point or a principal focus. Since there are two principal foci, we represent each one of them by capital F1 and capital F2. The distance between the optic center and the focal point is called the focal length. It is represented by small f, image formation by spherical lenses. Now let us learn the nature, size and position of the image when object is placed at different positions in front of the lens. Now let us look at this table. Position of object, position of image, size of image and the nature of the image. Let us take the convex lens. Let us place the object at infinity. Then the image is at focus f2. It is highly diminished and point sized. It is real and inverted. Let us place the object beyond 2f1. That is, the image is formed between f2 and 2f2. The size is diminished and the nature is real and inverted. Let us place the object at 2f1. Then the position of the image is at 2f2. Size is the same size as that of the object. It is real and inverted. Now let us place the object between f1 and 2f1. Position of the object is beyond 2f2. The size is enlarged. It is real and inverted. Now let us place the object at focus f1. The position of the image is at infinity. The size is infinitely large and it is real and inverted. Now let us place the object between f1 and the optic center O. Position of the image is on the same side as that of the object. It is enlarged but virtual and erect. Now let us learn the nature, size and the position of the image for different positions of object for a concave lens. Position of object, position of image, size and nature of the image. When the position of the object is at infinity, then the image is formed at focus f1. The size is highly diminished and point sized. Nature of the image is virtual and erect. The object is now placed between infinity and the optic center O. The image is formed between f1 and the optic center O. It is diminished in size, it is virtual and erect. Now looking at the table, we can conclude that concave lens always produces a diminished, virtual and erect image irrespective of the position of the object. Ray diagrams. Now let us study the image formation by ray diagrams when the object is placed at different positions in front of a spherical lens. The rays of light from the object, which are parallel to principal axis, after refraction from a convex mirror, meets at a point called focus, which is placed on the other side of the lens. In case of a concave lens, it appears to diverge from the focal point, which is on the same side as that of the object. A ray of light passing through the principal focus after refraction from a convex lens appears to be passing parallel to the principal axis. A ray of light appearing to meet at the principal focus of a concave mirror will emerge parallel after refraction from the concave mirror. A ray of light from the object passing through the optic center will emerge without deviating, irrespective of convex or a concave lens. Now let us study the image formation by a convex lens. Let us place the object at infinity. We get parallel beam of light parallel to the principal axis. After refraction, they meet at the focus f2. It is highly diminished and point sized. It is real and inverted. Now let us place the image beyond 2f1. Now let us take a parallel beam of light to the principal axis and a line passing through optic center. After refraction, they meet at a point where the image is formed. It is between f2 and 2f2. It is diminished and it is real and inverted. Now let us place the object at 2f1. Now let us take two incident rays parallel to the principal axis and one passing through optic center. After refraction, they meet at a point which is at 2f2. It is as the same size as that of the object but real and inverted. Now let us place the object between 2f2 and f1. Now let us take two rays parallel to principal axis and passing through optic center. After refraction, they meet at a point and they form the image beyond 2f2, which is enlarged, real and inverted. Now let us place the object at f1. Let us take two incident rays parallel to the principal axis and passing through optic center. We observe that these lines after refraction never meet. So we say the image is formed at infinity and it is infinitely large, but it is real and inverted. Now let us move on. Let us place the object between f1 and the optic center O. Now let us consider two rays parallel to principal axis and one passing through optic center. These lines never meet after refraction, but when projected backwards, they meet behind the mirror. So, the image is formed on the same size as that of the object. It is virtual, erect and enlarged size. Now let us see the image formation by a concave lens. Let us place the object at infinity. We get parallel beam of light which is parallel to principal axis. Now the image is formed at f1, focus. It is highly diminished, virtual and erect. Now let us place the object between infinity and O. We observe that let us take two rays parallel to the principal axis and through optic center. After refraction, they meet at a point. At this point, the image is formed. It is diminished but virtual and erect. Sign convention for spherical lenses. We are familiar with the sign convention of spherical mirror. Similarly, we follow the same conventions for spherical lenses too. But the focal length of a convex lens is taken as positive, whereas the focal length of a concave lens is taken as negative. Lens formula and magnification. Lens formula is given by 1 by V minus 1 by U is equal to 1 by F. We are familiar with U, V and F, where U is the object distance, V is the image distance and F is the focal length. While measuring all this, we follow the sign convention. Magnification. Magnification is given by the ratio of height of the image by height of the object. M is equal to height of the image divided by height of the object. M is equal to h prime by h. We can also represent magnification as M is equal to V by U, where V and U are the image and the object distance respectively. Power of lens. The extent of convergence or divergence of a lens is determined by its power. Power of lens is defined as reciprocal of its focal length, that is, P is equal to 1 by F. The SI unit of power is diopter, represented by capital D. 1 diopter is equal to the power of lens with the focal length of 1 meter. So 1D is equal to 1 meter inverse. Power of convex lens is positive and that of concave lens is negative. Hope you all understood the phenomena of light, which is the reflection and refraction. Now let us move on to the next chapter. Please keep watching Succeed e-learning app.